Hi, welcome back. This is the third lecture about simulating magnetic reconnection. In the first lecture, we look at the basic technique to simulate magnetic reconnection. This technique is called particle-in-cell methods. In the second lecture, we look at how we can implement a particle-in-cell method, and we look at code called IP3D, and a version of IP3D called the Sputnik. We also look at how to set it up an input file for a Sputnik, and how the configuration of magnetic reconnection is working. So this lecture we are focusing on actually running a Sputnik and produce simulation of magnetic reconnection. So the first step we need to do is actually to download the code and unzip it and have in the folder. Once we have the folder that is expanded, I'm giving here an example. I'm in a directory called Sputnik where I have the source code. The next step that we need to do is actually to compile. To compile the code, we use a script that goes under the name makefile. So we give a command to basically read a file that is called makefile, and then compile each part of the source code. So let's look at how this works. So I go there. I just need to type make, and you see that it's calling the compiler that on my laptop, that is C++. So here there are a bunch of warnings coming from the compilers. They are not important, just try to do some advanced stuff. Then I try to run my code. So I produce an executable called Sputnik, and then I give in the command line the name of the input file. In this case, jam_2d_imp, enter, and then the simulation is actually starting. So you see there is a simulation initialization at the beginning. We're presenting all the results, and then we start reiterating about the peak cycle. So here is an example of what has been done at the cycle of a particle in cell. So the first step, remember, is the particle mover. The particle mover function, we call it 4 times for each species. We have 4 species in magnetic reconnection simulation. So the first one is a 0, that is electron, and then we can also set it up the number of iteration in the predictor corrector, and we set it up to 3. The second one is the species for the ion, so it's species 1 is the current state species. And we have a mover iteration. We set it up just one iteration of the predictor corrector. So why electrons have 3 and ions have 1? Well, the reason is that the ions are 64 64 times larger than the electrons. So when the electrons they're quite light, so they move quite fast. The inertia of the ion is quite high, so they move quite slow. That means also that when we calculate the trajectory, we don't need to be so accurate, because the movement that they do is quite small compared to the electrons. So these are the 2 first species on the background, and then we have other 2 species that the first 2 species are the current state, and the second 2 species are the background. So the species 2 is electron, the background, and species 3 is ions in the background. The second step of the particle in cell cycle is the interpolation particles to the grid. So we go through each particles, and then we deposit charge, current, pressure tensor on each node of our grid. We have the divergence cleaning set up to ensure that the Gauss law is actually satisfied. So this is solved by using a linear solver called conjugate gradient. So the short is CG. So we do a Poisson. We solve a linear solver called the conjugate gradient CG, that is iterative solver. So we provide an error after it stops. So the error here, the tolerance we give for the errors is 1 to the -3, and it converges after 14 iteration. Then we use the Maxwell solver to calculate the electric field. In order to solve it, we use a generalized minimal residual linear solver called GMRES, right? So also the GMRES is a iterative solver, so we provide a tolerance to converge, and as you can see here at the beginning, it converges only after 7 iteration, right? So these two parts here, divergence cleaning, are two linear solvers. The first one, ECG, is a faster method because the Poisson problem is semi-definite positive, so you can use it. The generalized residual method, GMRS, is much more general than ECG. It applies not only to symmetric semi-definite positive problem, but also to general problems. So in the case of Maxwell solver here, we have a rather complicated solver that is the solver for the implicit method. So we need to use something general to solve it. And then after we calculate the E, the electric field, we basically update the B using the Faraday's law. So this cycle is repeated. If you want to complete the whole simulation that have been presented here, is basically 3000 cycle. Is roughly going to take you, between 30 minutes and 1 hour on your workstation on the laptop. So I did this simulation before, so let's see what is produced. So once you have produced the simulation, you will have a bunch of VTK files in your data directory. Remember that you can set it up the name of your directory where you want to save your output in the input file. So our input file has a data as a directory. Make sure to have the directory called data in your Sputnik folder, right? If you don't have that folder, it's going to continue but not producing any output results, right? So there are a few things that are in this data. So each cycle we will have the magnetic field, electric field, and then we have the charge density for the species 0, that is electrons on the current sheet, the charge density for species 1, that is the ion current sheet. And also we have the total, we sum it up these two density to have the net density. We save these quantities each 10 cycles, so you will have 0, 10, 20, 40, 60, 80, and so on until 3000. And so you will have a bunch of files. We also have a file that summarizes all the parameters that we have been using in the simulation. So how do we visualize these VTK files that are major output of Sputnik Peak? Well, so we do that by using a tool called ParaView. You can go to the website paraview.org and download the tool. There are different versions and different binaries for different computers, so you should not have any problem in installing. So once then you install it, you open up, and this is basically the major window that you have. So what we want to do is actually to open our file and visualize it. So let's see how this works. So what I do, I just open here, and then I go in directory with all my file, and you see that it collects the same kind of file at a different time step. Let's go a little bit slower. Let's see here. So as you can see here, it collects all the files under the name. So these are all the files with the same name at different cycle. So one nice thing about a ParaView is that we can open up in just one step all these different files, right? And then use this button here to make to show different time step of the simulation. So let's go back in the mode. So let's see again how this is working. I do file open, file, and then different file. You can see, I can click and see. I decide to open row I, that is the density of the I, and then you always need to do apply, and this is basically what you're going to have, right? And then you can here press the button and you will see different time step. Let's see just one more time. So we open, we select the quantity that we want to show. In this case, I'm going to show row I do OK, and then remember to push apply, and we will visualize. I added some more things here, like a grid and spaces. You will got this right away. And then we can start this button to make the simulation going on from 0 to a certain. So here I have a 300,000 because it is 3,000 cycle. So we can show. Right. So let's now to do the real meat of this lecture, that is to look at what are the results of the magnetic reconnection. So what I've been doing here is actually to load the information about rho E. So this is the electron charge density of the current sheet, right? So how this actually is working. So if I visualized, you will see that it looks like a small bands in the middle, and this color is correspond to a minus number. So why is a minus number? Well, because these are electrons, so the charge density is negative, right? So that means that in the middle we have a high negative charge density. So this is a signature of our current sheet that is coming out of the plane, right? So the way that is looking is just as band is very negative, right? So if we multiply this number by 4 pi, we will get 1.0 that corresponded to the initial normalization that we have. So the charge density in the middle is going to be 1 if you we just need to do an extra step of post-processing and multiply by 4 pi, right? So that's how is working, and let's see what I do. So here I just start visualizing. So this is going to open up all different rho E at different time step. As you can see, so the major results of the magnetic reconnection is that when it comes to density, is to break it here in the middle, the reconnection current sheet, right? And you see that is attaining. This is because also we added one perturbation in the middle to make much faster. So the reconnection starts quite slowly. You see that the region in the middle is actually thinning, but very slowly. So the reconnection started, but is still very weak. So we need to wait. Roughly here at the time we are still 120. We will see around to a cycle 2000, so around 200. The simulation going faster. So let's take control of the video itself. So you see here around 235. So you have a nice empty zone, right? There is no much electrons anymore. So let's see how this evolve. You see also, so this region is actually thinning, right? And then here you have the bulk of the reconnection. Just so you see that is way thicker than here. So you see you have some plasmoid coming here. You see that basically now in the middle is the density is very low, so there's no much and basically the plasma is moving one direction here and one direction here. Right. So was the when it comes to the row E. So this is the current sheet. Let's look at the most iconic figures of magnetic reconnection, that is the out-of-plane magnetic field. So here we have a cartoon picture of magnetic reconnection when is going on. So these we have the diffusion region, we have the two separatrix dividing the two different topological region, and then we have here in the red dash basically a family of currents, right, and that are going this direction. So each of these current flow creates an associated magnetic field that is out of plane. So these currents are in plane and it will create the characteristic feature. So let's look at this part of the plot. So we have this current going this direction that is going to create a magnetic field out of plane. On the bottom in this cartoon figure we have a current going in the opposite direction that it creates an auto a magnetic field that is going in. So here you say plus minus for the BC. So the right part of the cartoon has the symmetric feature. So the current here is going direction. So the is in going towards the slides, and then on the bottom is outside. So this is a characteristic quadrupolar structures. That means that you have we have plus, minus, minus, plus, right? So we expect to have these two guys to have them, approximately the same value, since the currents are the same, and this one have the same values, but in opposite direction. So let's look at how this looks like in the magnetic reconnection simulation. So here is the simulation. I'm starting from the time step 2000. Since we are saving every 10 cycles, here is 200. As you see, this is the BZ, and so we have the plus that is coming out of the plane, and then a minus that is going in the plane. So here we select the B, and also one important thing you need to do here. So B has the three components, but also the magnitude. So here you need to select BZ, right? If you want, you can also visualize BX, BY, but just switching here, to BX, BY also allow you to plot the magnitude. But since here we are after the whole magnetic field, we want to visualize the Z component. So let's see how this is evolved. So here I start the simulation, and you see here the cycle is going up. So here is our X point. You see that something is starting going on. These quadrupolar structures, so minus, plus, minus, plus. Right? So the magnetic reconnection is kicking in, and you see that the current system also is starting being quite well defined, and you see the formation of this whole magnetic field structure, right? So here basically we are at the end of the simulation. You see this quadrupolar structure here, and here, and here, and here. Here's the X point, and then here we basically have our reconnection jets coming out from the X point that we saw in the previous video. Right. So here is again. So the last quantity that I want to check that is extremely important, right? Is at least as important as the whole magnetic field when it comes to magnetic reconnection. So one of the results of magnetic reconnection is the formation of out of plane. So in our simulation is going to be not out, but is going inside the plane. So here you see this electric field, and then we have the magnetic field here from the lobe. So these are the asymptotic magnetic field. And then the E cross B basically drives the plasma to the X point. So the electric field, this outer plane electric field is driving the dynamics of magnetic reconnection. So it's a result of magnetic reconnection, but also driving the magnetic reconnection. And it also is very important when it comes to simulation, because it gives us the reconnection rate, right? So it gives, by monitoring what is the value of the outer plane electric field in magnetic reconnection, we can estimate the reconnection electric field. So that we can estimate how fast is the magnetic reconnection. So for instance, we can check what is the value at the beginning simulation, and we see that will be basically some noise for a long time, and then when our reconnection start, it will basically jump up, right, to a value, so the reconnection is going up, and then is going to saturate to one value. So you know that this value normalized to that fan velocity multiplied by c is 0.1. So we can recover this reconnection rate, but basically monitoring the value of the electric field here in the middle. So let's look at how this looks like in our simulation. So here I'm using a ParaView. I loaded the electric field at the different times. I selected the Z component among all the components that I can choose, and then I start here the video from the 200. So I just avoid all the first part of the reconnection where the reconnection start going, but is still very slow. I just go directly. So as you can see here, the beginning is quite noisy. You see the noise here coming from the fact that this part is the higher density for them. So this is the current shade. So we have a higher density. So we have a higher. We have oscillation with a higher amplitude. Right. So the reconnection in this electric field in this setup is supposed to go in. So we're going to expect some blue area here emerging during the simulation. So let's start the simulation. I start here, plug it in. You see that these are the results at a different time. Let's keep monitoring here. You see that there is something going on. Yeah, so you see reconnection electric field start appearing in the middle, right? And you see there. This point is basically stabilized as the value is expanding because it is right. So basically here this is the results of the end. So here we have a quite spread reconnection electric field as a result of the magnetic reconnection. If we actually monitor, if we take this point here in the middle, and each time we get what is the value of the electric field, we will be able to get the reconnection rate for our simulation. Then we can also plot the curve that you see in many of the paper that you have been studying. So this is I hope to have given you like an overview of how to do simulation of magnetic reconnection, basic tools from particle in cell, basic codes like Sputnik Peak, and basic tool to visualize like the ParaView. So what I would like you to ask is actually you can repeat the simulation that I've been showing you. And get the same results that I've been showing in this last lecture. So one thing I would like to suggest you is actually to do some more experiment. So probably the most interesting experiment that you can do is actually start from the simulation that I've been showing you, change the input file and try to simulate a simulation to which a guide field has been superimposed. So the guide field is the autoplane magnetic field that can be added. So this is often used for instance, to simulate magnetic reconnection at the day side, right? Without a symmetry in the density, but there is a guide field component. So how do we do that? Well, the only things we need to do is basically to change the input file. We don't need to recompile or do anything as far as you compile one time. So you go to the input file and you see there is the top of the input file. You will have B naught X, B naught Y, and B naught Z. So at the beginning, in the simulation I've been showing in this lecture is only has set it up B naught X. So what we can do is to set it up B naught Z to 0.095. That is equal to the value of the asymptotic value of magnetic field, right? So the magnetic field going in the X direction. So we put a magnetic field, a guide field that has an amplitude equal to the asymptotic field. Because we change the magnetic field, then we also change the amount of current that we need to put in the system to sustain the current shift. So also you need to change the drift velocity when it comes to the z component of velocity for the current shift species. So this is electrons and this is ion. We distributed the current between two species in this way. So I strongly invite you to try to install it, run it, and if you can also try to play with it. Simple things is just to simulate magnetic reconnection with a guide field. So what you can do is to repeat exactly the same diagnostic. So you run the simulation and then you use ParaView to investigate different quantities. So what you can do by looking at the output file is how the whole magnetic field change. So you probably from your study you know what is the impact of the guide field on the whole field structure. So you have a mean now to check how this actually can be shown in simulation. You also can check the reconnection electric field change, right? And you also can compare how the reconnection electric field is different from the case without the guide field. It's faster, slower, you get a feeling about it. Also, you can imagine, some other quantities that you might want to check in when doing simulation of magnetic reconnection, and you might want to output using ParaView. So this is my slides. I hope to have conveyed you, some exposure to some of the tools that if you're doing simulation of magnetic reconnection, you need to learn about. So this is the last slides, and hopefully everything you get a big picture of what a person doing simulation of magnetic reconnection do typically in his or her job. Thank you very much.